Welcome to CS 402 on Wednesday, June 11, 2014.
All right, warm-up number 2 is due in a little over a week. All right, the class has started. If you want to talk, please talk outside and then come back in, all right? You must implement from scratch, and again, it's the same reminder as last time. I strongly encourage you to work with your potential partners. And make sure you don't copy from code from the previous semester. And a reminder, the grading guideline is the only way we will grade. So I strongly suggest you to look at the grading guidelines first before you finalize your program, because the grading guideline might change your mind how you want to implement your code if you intend to get 100%. Because if you do it the wrong way, later on you're going to find out that you're going to lose a lot of points from the negative points section of the grading guidelines. Okay. Because I try to discourage you to use arrays. Okay? If you start putting any arrays in your code, you're going to find out your code is going to crash left and right because of the way we're going to grade. So I was just looking at the grading guidelines, and I'm going to make a few changes over here. This is at the top of the grading guideline for the plus points. So what I'm going to do is that, I want to cut down some times on the grading time. Because running through all these programs take a long time. So what I'm going to do is that I'm going to reduce some of this, some of these lines over here. Okay? So most of the stuff is going to run from trace files. Okay? So you're going to make sure that your trace file works perfectly. And I'm also going to, change the order of some of the command line arguments, swap them around. Make sure that you know how to handle lots of command line arguments. Okay? So I will update only this section after today's lecture. Okay, the rest, the rest you need to look at them and see, especially the cases where there are gazillion, packets are going to arrive, or the packets are going to arrive at a very fast rate or very slow rate. These kind of cases. Make sure you use the right kind of data structure so you don't, crash your program, right away. All right, so again, we can only use one grading policy for everybody, okay? And please install Ubuntu 12.04. Has everybody installed Ubuntu 12.04? Anybody hasn't done it yet? Okay, if you haven't done it yet, you should do it, very soon, because once the kernel assignments start, you really don't have time to start wasting, days on getting Ubuntu 12.04 to work. Okay, if you have trouble, come to see me, come to see the TAs. And again, the TAs, we are, I guess, I'm here, mostly only Monday and Wednesday, and the TAs have their office hours. So if you try to make appointments with them outside of their office hours, you really need to do it like a day ahead of time, okay? And try to find a time that you can meet, okay? So try to get all this going as early as possible. All right. By the way, the other one is the same one. Anybody who hasn't signed it yet, please come and sign it now. Okay. So we'll continue to go pretty fast. Try to get you ready for kernel 1, and that means I guess section 5.1 of the textbook. Okay, so we're in chapter 3. We're going to try to finish the main part of chapter 4 and go into chapter 9. Chapter 3, last time we saw how to do context switching, and I mentioned that the thread switching is very similar. I guess we were at this slide. Okay, talking about what a thread looks like. Okay, so today we're going to look at the code. How do you switch from one thread to another thread, pretty much without involving the operating system. Okay, so we want to make you understand that thread switching is pretty much like a procedure call. All right, but it's a little weird, right? Because you think about running thread. How do you switch from one thread to another by making a procedure call? Okay, so here we go. All right, so we have a function over here. This is the function. All you need is this function to switch you from one thread to another. Okay, so it's pretty magical. All right, so think about you have a thread of execution that's running the CPU, right? So over here I have the CPU right here. Okay, and this is the current thread, and we're going to pretend the current thread is some sort of a global variable. Okay, so if you are within your own process, this global variable might actually live in your address space. So if you accidentally wipe it out, then of course your program is not going to work. Okay, so inside your address space, there's a global variable called current thread, and that one is going to point to the thread, the TCB, the thread control block of the currently running thread. Okay, in this example, we have two threads running. One is the one that's going to call this function. That one is going to give up the CPU. Says, for example, it's waiting for a mutex. So therefore, it says I'm going to give up the CPU. And I'm going to switch to whatever thread that's available to run. Okay, so this is thread A that's running the code. Thread B is the one that's coming in. So this guy, the next thread is thread B. Okay, so you want to switch from thread A to thread B. Okay, so first of all, if you are switching from thread A to thread B, that means that thread B is suspended. So if thread B is suspended, then the context of that thread is consistent with the current state of that thread. Okay, so if you look at thread B, right? Thread B inside the thread control block, we mentioned there's something called a context, right? There's a region that you store the context. Okay, the context is the one that you save when you suspend the thread, and if you need to continue to execute that thread, you need to restore from the context. Okay, so the context of that thread is going to say, well, thread B is right here. Okay, it has a stack, right? All these things belong to the same address space. Okay, so inside the thread control block, it tried to remember what the state was. And one of the state was where is the top of the stack for the thread B. Okay, so therefore over here there's going to be this data structure is going to have a field called SP, the stack pointer, that remember where the stack pointer is supposed to be. Okay, so therefore this memory location is going to contain a pointer to the correct place for thread B stack pointer. Okay, so thread B is right here. Then the stack pointer will point to the top of stack for thread B. Okay, and thread B is suspended, so all these information are consistent. Okay, so this guy points right here, and thread B, start from main, call some function, and eventually it's sleeping. Okay, so over here I put question mark because I don't know what these functions are, but I know that thread B is suspended. Okay, so therefore in the thread control block, in the context area, the stack pointer will remember that it's pointing to this place. So therefore later on when you try to run thread B again, you better put this into the CPU so that the CPU will point to the right place. And also you need to put, wherever you store EBP, and you got to put it in the right place in the CPU, so this guy will point to the right place before thread B can execute. All right, so we're going to come back to that after we start executing the code. Okay, so right now we need to know that thread B, the data structure is in a consistent state. All right, so later on, when we try to put thread A to sleep, we also want to make sure that thread A, when it goes to sleep, the data structure is also in a consistent state, sort of looking something like this. All right, so keep that in mind because we got to make sure that that happens. All right? Okay, so thread A is ready to go to sleep. Right, so over here, this picture says, well, maybe thread A just called pthread mutex lock. Okay, and then the mutex is not available. So thread A is going to say, well, I'm going to put myself onto the mutex queue, right? Remember, that's what it means to wait for a mutex. Every mutex has associated with queue. If you don't have the mutex lock, you get on the queue. Okay, so thread A has already put itself onto the mutex queue, meaning that its thread control block onto the mutex queue, and now it's ready to go to sleep. Okay, so it's going to look for inside the data structure to look for who's the next thread that's ready to run. Oh, thread B is ready to run. So it's going to put thread B's thread ID into this data structure. into this function argument, say now I'm going to switch to thread B. All right, so then it's going to execute this code. Okay, so let's see how this code works. All right, so this code, just like any other C function, okay, when it gets compiled into machine code, it looks the same way, right? Push EBP, move ESP, EBP, and then the main part of the code, okay? This one has a function argument, okay? So the stack look like the way that we talked about last time, okay? It has a function argument. It has no local variable, okay? In this case, they actually need to save one register, say, push ESI, okay? But it doesn't need to increase space for local variable because it has no local variable, okay? And then in the middle, it's the thread code. It's the code right here. When it's done, what it's going to do, return just like any other C function. Return, right before you return, you restore the register, you pop EBP, and then you return. All right. So I'm not going to explain this again because we covered all this stuff in the last lecture. All right. What you need to remember is that every C function is going to look like this. Okay, but unless you have a special case where you have a function that has no argument and no local variables, and it doesn't really save any register, then in that case the stack only has the return address. In that case, yeah, the code might be a little different. Okay, but otherwise, any normal C code will look like this. This is the beginning and this is the end for any kind of if you look at the assembly instructions. All right, so let's execute this code. So you're in pthread mutex log. You found out who is the next available thread to run, and then you call switch to switch to that thread. All right. So what happens over here is that you're gonna make a function call, right? So you're gonna push. You're gonna create the stack frame for switch. I mean that's how you call switch, right? You're in mutex log. You're gonna create the stack frame for switch. Okay, and that's at the entry point of switch. Okay, so on entry point of switch, the callers register are saved, right? So it looks like the following. After you call switch, at the beginning of switch, okay, the stack changed to a point that this guy is switch. Okay, so we're still running thread A, right? So therefore, ESP is going to point to the new top of stack. EBP is going to get point, somewhere in the middle of the stack frame, right? That's how EBP works. Okay, the current thread still points here. And this guy, over here I said the stack pointer inside the context is question mark. Why is that? Okay, because this is the current running thread. When it's running, then the thread, in the context area of the thread control block doesn't really reflect what's going on with this thread. When this thread gets put to sleep, then the context is going to be the last place where this thread get put to sleep. Okay, otherwise the data structure might be out of whack, and that's okay. All right, only the thread that's suspended has the correct information in this data structure. All right, so now you're here, and then we're going to execute the next instruction. Okay, the next instruction says current thread SP is equal to SP. Right, so what happens over here is that the current thread is this guy, right? It points to thread A's thread control block. It actually points to the the context area in the thread control block, but we're sort of making the code a little simple. So there's a field over here called SP. It gets the SP, right? So this SP is the SP of the CPU, that's currently in the CPU. Okay, so the idea over here is that ESP in the CPU currently points right here. So you take the content of this guy and you just copy into this memory location. All right, and what's the effect of doing something like that? Well, the effect of doing something like that is that, this guy will now point to the same place as the top of the stack, right? Okay, so when you finish doing that, it's going to look like this. Okay, so in this picture, right, this thing points to this location now, or because you just copied this value into here, that means that both pointers point to the same place now. Okay, so this is how you try to save the context into the context area of the thread control block. Okay, we showed an example how to save one thing. Okay, and that's the stack pointer inside the CPU. Okay, so we copy this into SP over here. Okay, we're ready to execute the next instruction, right? The next instruction says current thread equal to next thread. So what does that mean? Right, that means that you get rid of this and you point to that. All right, so that's what it means. Current thread equal to next thread, and boom, we have this. All right, the next instruction, SP So by the way, at this point, current thread pointing to the next thread. Which thread is executing? Is thread A executing or thread B executing? A. Anybody thinks thread B is executing? Right? I mean, it's the same thread of control, right? I mean, if you look at the code, right, thread A is executing, is calling this function, right? Okay? So a thread of control meaning you follow the machine instructions, you execute one at a time, right? So we are executing thread A. Okay? So now even though the current thread says we are, this is the thread B is the current thread, so it's kind of weird that we're still in thread A. Okay, but so keep that in mind that we're actually in thread A, or if you argue that we're in thread B, well, if you're in thread B, then the stack pointer of thread B needs to point to thread B's stack, right? Otherwise, how is it in thread B, right? When thread B is executing, okay, the instruction pointer needs to point to, the code segment, and the stack pointer needs to point to, the stack of that thread. Okay, so right now, if you look at the stack pointer is pointing to thread A stack. So we're really not quite in there. Okay, so there's some inconsistency here, right? Current thread point to thread B, but the stack pointer point to thread A stack. All right, so that's why we need the next step. SP is equal to current thread XP. Okay, where's current thread XP? Current thread, you follow this pointer, it's thread B's, thread control block. Okay, now current thread SP, now you're talking about this guy over here and not this guy. Okay, so we say inside the CPU's ESP is going to get the content of this one. So you copy whatever that's over here into the CPU. All right, when you copy whatever that's over here into the CPU, what happens? Well, this guy will basically point to right here. Okay, so you get to this picture. Okay, now are we executing thread A or thread B? Well, I mean, actually we're executing both, right? I mean, thread A is still executing code, right? But if you look at the data structure, the current thread is pointing to thread B's thread control block, and then the stack is pointing to thread B's stack. Well, so we are also executing thread B, right? So it's kind of hard to say which one it is. Okay, but you sort of know that we have already switched to thread B. Okay, so why is it that thread B returned to where we left it off? Okay, and the reason is that we have just restored the context of thread B, and thread B start executing, which means that the last, the top of the stack frame for thread B, the one that I put a question mark there, it was also switch. Okay, the top of the stack frame over here, I put a question mark there on purpose, but I know that that particular stack frame is switch. Okay, so thread B, basically last time when it left off, it was left off right over here, inside the same function. So thread B, when it tried to give out the processor, it also calls switch to switch out of the context, because right now if you look at thread A's data structure, it looks exactly like what thread B has before, right? In the context area, the stack pointer points to the top of stack. The top of the stack is switch. Okay, where's EBP? Right, EBP is saved right in the stack frame, right? For thread A, EBP is saved in the stack frame. So therefore, you can also conclude that for thread B, EBP, the old EBP is also saved right here. Okay, there's also save registered over there, so they will get pop. The example that we saw, ESI is going to get pop, to restore back into the CPU. Okay, so now you're executing thread B. Okay, you're almost right there, right? The only thing that's out of whack is EBP, right? At this point, EBP in the CPU points to, somewhere in the middle of the stack for thread A. So over here, again, we're not really quite completely in thread B yet, but then we're also not in thread A. We're somewhere in limbo. Okay, and then we're going to execute the next instruction, right? That will complete the entire transaction. Okay, next time we're going to call return. What happens in return? Right, you pop EBP back into the CPU, right? That's what return does, right? Return does two things. Right before the return, there's a machine instruction. Okay, so this return at the C level, okay, can compile into two machine instruction, right? Should we go back there and take a look at that thing again? Okay, so over here, these are the two instructions. Well, actually, in this case, since there's a pop register, there are actually 3 machine instructions for one C-level instruction called return. Okay? Even though we don't have this, the last instruction over here is return, so return is going to get executed. I put a return over here, so that I can point to it. Okay? But this thing get compiled into 3 machine instructions: popping ESI, restoring the register, moving EBP from the stack, or taking whatever on the stack and pop it into the EBP register of the CPU, and then return is the same thing as taking the top of the stack and use that address at the top of the stack as a return address and pop that into EIP. Okay, so this return instruction, it changes EBP and it also changes EIP. Okay, so over here, where are we? Okay, so this particular return instruction, okay, so what happened is that it sets EBP, right? EBP was pointing right in the middle of this stack frame. Okay, now when you're executing this instruction, EBP is going to be pointing right here. All right, so now we are, thread B has all the CPU at the right place. Okay, and what does thread B do, the next instruction? Well, the next instruction thread B does is again, it's the return machine instruction. Okay, which pops the instruction pointer or the return address in the stack into the processor. Okay, so when we return the top stack frame, this one used to be switched, right, to get popped, and now we are back into the procedure that calls switch. Okay, is this pthread mutex lock? It doesn't really have to be. It could be condition way. It could be, I don't know, anything that caused this thread to give up the CPU. All right, so this can be condition way. It could be pthread mutex lock. Could even be things like, waiting for I/O to do a read or write or something like that. So that's why I don't really know what this is. Okay, but now I know that, this guy continued to execute. All right, so this is how you switch from one thread to another without getting even the operating system involved. Okay? All right, so over here it says, well, if the thread control block were user space data structure, then the switch, this code, no operating system, right? Even though you're manipulating the CPU registers, okay, but when you manipulate the CPU register, you don't require the operating system intervention. All you have to do is execute code, okay? If you execute code properly, in this case, this code, turns out you can interpret that as switching thread from one thread to another. Okay, so this function is a little weird, right? What's weird about this function, right? This function, one thread, at the beginning of this thread, at the beginning of this function, one thread is executing, okay? Right at the point when it's doing return, then, or you can actually argue somewhere in the middle, the other thread starts to execute. Okay, exactly when does that thread start to execute? Well, you don't know because it takes several machine instructions to switch to the other thread, right? So therefore, you can argue that, well, at the time, current thread pointed to the other guy, while the other guy started to execute, but the other guy is executing exactly the same code as this thread, because all threads call this function to switch to another thread. Anytime you want to give up the CPU, boom, you go here, and you give up the CPU. So therefore, every thread, when they're suspended, if you look at the top of the stack of that thread, it's switch. All right, so that's why you can successfully, using the same function, to switch from one to another, because when a thread gets suspended, the top of the stack is always switch. Okay, so therefore, continue to execute this code. You don't really care whether you want to interpret that you're in the first thread or in the second thread. Either way, when you interpret it, they all work. Okay, the instruction pointer point at exactly the same place in the code segment. Okay, and all you have to do is, if you continue to execute that code and adjust the EBP and the ESP, then it all works out. Okay, so this is really tricky code. Okay, make sure you look at this a few times, make sure you understand it. All right, and that's how you switch thread. Okay, later on when you work on a kernel assignment, the first kernel assignment, you're going to implement kernel threads. Kernel thread is going to switch from one thread to another. Guess what the code looks like? Okay, it looks just like this. All right? Wow, it's a little more involved. When we get to chapter 5, we're actually going to see the actual code. Okay? But the basic idea is that, yeah, you can switch thread, doing something like this. All right, and here again is the reminder of that code, right? The C code get compiled into this. Okay. Okay, so you say, well, how do I regularly write C code to actually refer, the ESP register? As you look at the kernel code, you will see how that's being done. Okay, so there's actually a way to do this. All right, the slide we skipped, right? It's about Spark. It's different. All right, so that finished our second context switch, right? This is called thread coroutines because, switch from one thread to another, it's like a procedure call, so it's a routine. And these are cooperating threads. Okay, these threads are within your same process, right? So you write the code to control a bunch of threads. So all these threads are friendly to each other. You don't have to protect one of them from each other. You can switch from one to another by calling switch. Okay? All right, the next thing we're going to look at is system call. Okay, again, switching context now from user thread to kernel thread. All right, the system call, right, involve invoking the trap instruction. Okay, so over here it says, well, there's, it's kind of really no switching. Okay, because all you do is you make a function call, and these are system calls. System call is a function, right? Inside the system call, there's a machine instruction called trap. You trap into the operating system, so you're still the same thread that's executing, right? When you go into the operating system, your processor mode get changed into protected mode, okay? But in a way, you are still the same thread, okay? But then you can also say, well, you're really not the same thread because now you have to use a different stack. Okay, can the operating system, once you switch to the protected mode, you're executing operating system code. The instruction pointer is going to point to the operating system code for the trap handler. Okay, the trap handler is part of the operating system. Okay, so the instruction pointer has to point there, and now you become the kernel thread. Can the kernel thread use your stack? All right, some people say yes, right? But the kernel thread don't trust the user. Okay, the user, maybe you can write some assembly code, mess around with your, user stack, and you say, hey, operating system, use my stack. The operating system, no, I don't trust you. I have to use my own stack. All right, so in a way, yeah, the thread changes identity, so you're a different kind of thread now because you're using a different kind of stack. All right, it's very important the operating system uses a different stack. Otherwise, we're going to end up with all kinds of security problems, right? Because when you do execute return instructions, you're supposed to return to a certain place, and then there's stuff on the stack that you depends on in order for you to restore context. Okay, what if the user, makes some clever manipulation so that when you're supposed to return back into user space, you're still in the kernel, but the instruction pointer point to user code. Okay, and then you didn't really switch the machine mode back from protected mode to user mode. Okay, and then you're in trouble, right? So it's very important that you use a different stack in the kernel. All right, so the system call sort of looks like this. Okay, over here I say, well, a trap is a software interrupt. Okay, so I guess when we talk about chapter 1, we said that Unix signal is not a software interrupt, right? Signal is an upcall. So over here, I'm going to actually declare that trap is a software interrupt. Okay, the reason is that trap actually, when you execute a trap machine instruction, okay, it generates a fault, and the fault gets you into the CPU. Okay, so this fault actually looks just like an interrupt. Okay, when the hardware come interrupt your processor, okay, it's treated, exactly the same way as trap. So trap is some way, it's an interrupt that's caused by executing an instruction. So therefore, it's actually a software interrupt. All right? Okay, so the interrupt handler will invoke the trap handler. So you actually generate interrupt into the, into the hardware, and the hardware says, oh, which interrupt handler should I execute? Well, it's the one that corresponds to trap. Okay, so in the operating system, there's a bunch of interrupt handler. Most of them are for hardware, but one of them is for traps. Okay, so traps are handled just like interrupts. Okay, and then we're going to see how interrupt looks like. But we're going to start with trap. Okay, so over here you have a program running over here, right? I mean you have a thread executing this code. This code called write. Write is a system call. It's a wrapper around the trap machine instruction, right? So therefore you do something over here, and then eventually you call trap. Okay? So at this point, the user stack sort of look like this, right? You have main over here, you call, program, and then eventually you call write, and at this point, you trap into the operating system. Okay, so at this point, there's a switch, from you to the kernel thread, right? The CPU mode is changing to privilege mode, and you're going to end up switch to a different stack. Okay, so inside the CPU, the ESP was pointing right here. Okay, and all of a sudden, when you go into the kernel, ESP points to the kernel stack. All right, so this particular trap instruction, actually, when you execute this, right, multiple things happen, like an atomic operation. Okay, changing EIP to kernel code, changing the processor mode to protect it, changing ESP to point to this thing. There's a lot of stuff that happens. Okay, so it's really not one instruction that makes this happen. It's actually a few things that happen together. And collectively, these things are called the hardware abstraction layer. Okay, so the hardware abstraction layer is something that abstract away the hardware from the operating system, right? So if we look at this code, if this is user space, this is kernel space, right? It used to be that we draw hardware down here. Okay, as it turns out, there's another layer down here right before the kernel and the hardware is called the hardware abstraction layer. Okay, so this one makes you eventually transition into running kernel code. Okay, and the reason we sort of don't describe this very much is because this is hardware dependent. Okay, and it can also even be a machine configuration dependent. All right, if I want to build a machine, right, inside the machine there's a CPU, but there's also a bunch of chips that goes around next to the CPU. Okay, if something are missing inside the hardware, right, so it really depends on what the machine looks like. Even though you're using exactly the same CPU, you might have different chip in your system. So some of the chips that are missing, then they might have to be emulated in hardware. So therefore, they are done in the hardware abstraction layer. Okay, the point is that when you do something like this, then your operating system kernel can become more hardware independent. Okay, so this thing is really, depends on not only what CPU you're using, also what system you have. All right, so we don't really talk too much about it. We sort of assume that once you execute this trap, the trap is going to cause an interrupt in the hardware, and then some magic happen inside the hardware abstraction layer, and then boom, you are in the interrupt handler routine. Okay, so some of this magic that happened is about saving the user state, right? So the user context needs to be saved, so it's saved somewhere. Okay, so later on when we need to return back into user, right, over here you call write, eventually operating system is going to finish the write and says, hey user, you're done with write, so you got to go back and execute this code right after trap. Okay, so therefore you have to restore the user process context. Okay, if you only have one CPU, right, at this point you're executing the user process, so the entire state of the user process needs to be saved in some context area. Okay, and then you go execute the CPU, which means that your CPU now is loaded with information that's required for you to run the kernel code. And eventually when that guy is done, it needs to unload everything from the CPU and then restore the context of the user, including the mode of the CPU. Okay, so all these things are actually quite involved, and that's why, they're all done in this extra layer. All right, I'm going to briefly describe what goes on this extra layer in a machine-dependent fashion. But please keep in mind that there's a lot of different things can go on right there. All right, so we're going to assume that the hardware abstraction layer take care of all these kind of stuff, and eventually you're going to start executing the interrupt handler, which is part of the operating system. Okay, so this is the sort of the hardware configuration independent interrupt handler. Okay, and start executing over here, and it says, well, what is the, how do I get to this interrupt handler? Is it because there's a hardware interrupt happening, or is it because there's a system call? Okay, so over here it says, if the interrupt code is a system call, which means that it you get into here because of a trap. Okay, so trap and system call is actually the same thing. Over here, it comes here because of a trap, then I'm going to call the system call handler, right? So ESP was pointing here, you call the system call handler, you're going to create a new stack frame for the system call handler, and then you call this code. Over here, you look at a bunch of trap code to see which system call did you make. Did you call write? Did you call read? Did you call fork? Did you call wait? Right? So the code over here tell you which system call did you make. And there's 256 of them because this guy is a single byte. All right? If the trap code is equal to write, you call the write handler. And finally, now you're inside the kernel trying to finish the write or trying to perform write for this user process. Okay, so the system call handler is going to call write handler. So ESP eventually is going to call over here, and then you will be writing, you will be executing code to handle the write system call. All right, so maybe the write handler, you can say, well, this is called K write for kernel write or something like that, or whatever it's called. Okay, so you're inside the kernel trying to continue the system call write. All right, and eventually when you're done, you finish writing, right? You take that data. Okay, so the data is stored in user space, right? So over here you say, right, there's a buffer. The buffer is actually in user space. So where does the kernel know where this is? Okay, so now the user process is suspended, right? So the entire user state is stored in some kind of a user process context, right? So the user PCB, the process control block, has some information about where that state is stored. Okay, so that's what all the setup here is doing, is try to set up the state so that when you go into the kernel can actually fetch those the parameter that get passed over here. Okay, so when you're inside the kernel understands the process control block, it understands the thread control block, it knows how to go through these data structure to find out where these guys are, what are the arguments, for this write. Actually, I only circle two things. I need to circle all three things because it actually tells you which file to write using integer, which is indexed into the kernel file descriptor table, right? So the kernel actually needs all these three pieces of information in order to find out which file to write to and what data to write to. Okay, so inside the write handler, that's what it needs to find out. Okay, and then it will go off, start a disk operation, copy that data onto the disk, and when the disk generates interrupt and says, I'm done, okay, at that point, the write is ready to return. Okay, so when the write returns, this function will return. Okay, so you pop this guy off the stack pointer point here, and then the syscall handler will return. You go back over here, and then you go to the interrupt handler, and this guy is going to return, but this guy's return is very special. Okay, the interrupt handler return is not like the other guy. The other guys are function returns. The interrupt, well, this is the top of the kernel stack. There's nothing beyond that. Okay, so over here, the last thing that you have to do over here is actually a return that returns you back into the user space. All right, so this return, it's a little more involved. Okay, so right before you finish doing over here, the user data is all set up inside the kernel because the kernel understands all the data structure in user space. Over here, this is a special return right over here. Okay, actually that's called something called IRET machine instruction. Stands for return from interrupt. Okay, so when you call return from interrupt, so basically what you do is you return back into the hardware abstraction layer. Okay, some magic is going to happen to copy all the return stuff back into user space. Okay, and then you're going to return back into user space. Okay, so all the user contact will store in a special place. Now it's going to restore from that special place so that the write can continue from over here with the data passed from the kernel back into the user. Okay, in this case, what does the kernel return to write? Right, well, when you do a read, actually some data needs to be copied. When you do a write, the only thing that you need to return is the return code. Okay, so again, return code usually set up in the EAX register for Intel processor. So, somehow this return code get returned back into write. So at this point, it will be able to return the return code for write. Okay, if it's an error code, then the error number needs to be communicated from the kernel to the user space. All right, so all these things need to be updated at the right place. And later on, we're going to get a little more detail, especially when you start implementing, the kernel code, then you will see all these things happening. All right? So right now, the hardware abstraction layer is kind of abstract, but that's the way it is. All right, a little more detail, right? So when you execute a trap machine instruction, you trap into the kernel. Over here, a little more detail is that the interrupts are disabled. Okay, so what happens is that when you trap into the kernel, since we are using the same mechanism as interrupt handlers for real hardware interrupt, if you don't disable interrupt at that point, what happens is that if another interrupt comes in, it will wipe out all your data structure. Okay, so they don't really share data structure very well, right? And we saw in interrupt, the way that you handle multiple things that can, use the same data structure in an interrupt is you disable interrupt. Okay, so over here, we're going to disable interrupt inside the CPU, right? Remember, inside the CPU, there's a flag register. Inside the flag register, there's an interrupt enable bit. So that bit is turned off to say not allow any interrupt because I'm in the middle of, doing something very important, okay, handling the software interrupt. So I don't want any other interrupt to interfere with this operation. Okay, so the rest are done with the interrupt disabled. Okay, so the processor is going to be set to the kernel mode. The hardware abstraction layer is going to save the IP and the SP. So these are the user processes, IP and SP, in some sort of a temporary location in the kernel space. Okay, if you Google this, you're probably going to see some, for some machines, they will use an interrupt stack. So, in order for you to execute this code, well, if it's code, you need a stack to execute. Okay, because we don't really want to write everything over here in machine language. We want to write these things in C. If you want to write any C code, you need a stack. So therefore, to execute this code with the interrupt disabled, the kernel stack is using the interrupt stack. Okay, so it's a special stack that you use temporarily. As soon as you re-enable interrupt, another interrupt is going to come in, it will reuse that stack. So you got to make sure that you clear out the stack before you re-enable interrupt. Okay, so you use a temporary stack, and again, this is processor and configuration dependent. Okay, exactly what's happened over here because it's part of the hardware abstraction layer. All right, additional register might be saved depending on what processor you have, depending on what kind of a hardware you have. Hell is hardware dependent and it's outside the scope of this class. Okay, so we're only going to briefly describe what it does right here, and you won't see the hardware abstraction layer again. Okay, we're going to assume that some magic happened over here for you to transition into the kernel. Okay? All right, so hell is going to set the stack pointer to point to the kernel stack designated for the corresponding user process. Okay, so now we want to transition into the kernel thread. Okay, so the kernel thread is going to use a real kernel stack in order to execute the interrupt handler. Okay, so over here, that's not the interrupt stack. The interrupt stack is a temporary stack. So you have to switch to, the real stack. You're going to pass some of the information from the user space into the kernel. So that means that you have to copy some of the stuff from the interrupt stack into the actual kernel stack. Okay, so once you determine which kernel stack to use, then some of this copying is going to happen. Hell is going to set the IP to the interrupt, sets IP to interrupt, and then, the interrupt handler is going to get invoked. And the interrupt eventually is going to call the system call handler. Okay, so at this point, you're leaving hell, leaving the hardware abstraction layer, and you're executing inside the kernel. All right? And all these stuff are written in C. That will pop the user IP and SP from the temporary location, which could be the interrupt stack, and push them onto the kernel stack. Okay, so that's how you transfer data from user space into the kernel space. Okay, and now they are on the kernel stack, so the kernel knows where they are, and they can start using them. All right? And at this point, on return, so after all these things is copied, then you don't need the interrupt stack anymore. Okay? Then you can re-enable interrupt. Okay, so it's important to copy everything off of the interrupt stack, put it into the kernel stack, so that only this thread has access to it. Well, actually, in the kernel, everything can access everything else. But the idea over here is that now you are executing the kernel stack on behalf of the user process, trying to help the user perform the right system call. Okay, so therefore, you have all the information that you need, and now you can enable interrupt. So if other people want to use the interrupt stack, go ahead. Okay, and there will be a separate thread of control that's executing for another thread. All right, so this thread will continue from this point on executing code while with interrupt being enabled. So this is how you get into, eventually executing the trap handler. All right? So this is, the system call context switching from the user context going to the kernel thread executing with the kernel stack, and with the information get passed from user to kernel. All right? And eventually when you're done, on return from the trap handler, you disable the interrupt. So basically you have to unwind everything over here. You have to copy the stuff from the kernel stack back into the interrupt stack, right? So first you disable interrupt, then you can do all that kind of copying, okay? and then you execute IRET on an x86 processor to return from interrupt. Okay, so again, this behavior is processor dependent. For an Intel x86, right, it will pop data from the interrupt stack back into the user space, and then eventually it will get back into the user space, change the processor mode, change the instruction pointer to point to the user program, and change the stack pointer to point to the user stack. At that point, you're executing the user process again. All right, so lots of stuff happening over here, and again, some of them are processor dependent, and they are configuration dependent. All right. Okay, so over here, the comment over here is that, the same sequence happen when you get a hardware interrupt. Okay, this whole thing, they all happen, except that the only difference is that instead of going to a system call handler, you go into an interrupt handler. Okay, otherwise, the entire thing is exactly the same. Okay, when you get a hardware interrupt, right, what was the CPU doing when you get a hardware interrupt? It's executing some thread, right? Okay, is the CPU executing a user thread or a kernel thread? Well, you don't know. Whenever the hardware, the hardware interrupt comes at a random time, it's asynchronous interrupt. You have no idea when the, when the user is going to press Control-C on the keyboard. I mean, that's an interrupt. Okay, the disk is going to finish whenever it finishes, and it's going to interrupt the processor. So yeah, your CPU might be in the protected mode, executing a kernel thread, or it might be, in the user space, executing in the no privilege mode, okay, in user mode, okay. One thing for sure is that the CPU is not executing this code right here, because this code right here is executed with the interrupt disabled, right? So if you have an interrupt happen at that point, with the interrupt disabled, the interrupt becomes pending, and eventually when the interrupt is re-enabled again, then the interrupt is delivered. All right, so when interrupt happens, the same thing goes on, except that, maybe such things are slightly different, because if you are executing kernel code, then some of the stuff from user to kernel transition doesn't really happen, because you're already in the kernel. Okay, but if you're executing user code, then exactly the sequence of things will happen. All right? Okay, so the big idea about context switch is that in order to perform a context switch, you must first save your context. And the reason you want to save your context is that because you want to go back to it, right? You want to go back to it. You want to go back to exactly where you left off. So you need to sort of figure out what are the things that you have to save in order for you to go back to exactly where you left off. Okay? And you want to save the minimal number of things because you don't want to end up copying too much stuff. Then, if you end up copying a lot of stuff, that means that when you perform a context switch, it will take you a lot of time. Okay, so as you can see, thread switch, procedure switching, does it take a lot of time? I mean, you saw the machine code already, right? Okay, so it's not too many instruction overhead. Okay, remember that for a particular function, right? In the beginning part, right? If we're looking at assembly code, the beginning part is setting up the stack. The end part is to restore the stack. Is to restore from the stack. Okay, so these code is considered overhead, right? Because it's really not the functionality of this function. Okay, so in order to perform context switching, you need to be able to return back to where you are. We have this overhead. Okay, for procedure to switch from one procedure to call another, the overhead is very minimal. Okay, what about when you switch thread? Well, we're using a function, right? So when you switch from one thread to another, the overhead is also very minimal. Okay, so therefore some people will call thread, lightweight processes, because it's really easy for you to handle many, many threads. Switching thread is really not a big deal. It's almost like a procedure call. Okay, what about system call? Is system call very expensive? All right, so again, go back to the slide. Okay, we don't really see the code, right? Because it's in the hardware abstraction layer, so lots and lots of stuff happen. Lots of stuff getting copied from one place to another. Okay, so the system call is very expensive. Okay, so we try to, minimize system call because every time you make a system call, things are going to be slow. Okay, so keep that in mind. Part of the stuff we're going to talk about to make the operating system running more efficiently is try to be clever about system call. Try to make sure that we don't trap into the kernel. If we trap into the kernel, it's going to be slow. All right? But, if your program do a lot of read and write, do you have any choice about trapping into the kernel? You have no choice, right? Because you want the service from the kernel to go read some data for you to write some data out, right? So you're stuck with that. Okay? But if we're doing, pthread condition wait or something like that, we try to say, hey, let's not get into the kernel, because every time you get into the kernel, it becomes really, really slow. All right? So keep that in mind. Okay, a little bit about interrupts, right? So interrupt is basically exactly the same as a system call. Okay, and a reminder, signals are generated by the kernel, they're delivered to user process. Okay, we shouldn't call signal software interrupt. Okay, interrupt are generated by the hardware, they're delivered to the kernel. Well, now we know that they're actually delivered to the hardware abstraction layer and then go into the kernel. All right? Okay, so when you have an interrupt, so now we talk about hardware interrupt, right? Hardware interrupt comes, your processor is executing something. It's either executing a user process or it's executing a kernel process, right? Or you're either executing a user thread or you're executing a kernel thread. Okay? When you're executing in the user thread, which stack should you use to handle the interrupt? Okay, the interrupt has nothing to do with the user thread that are currently executing, right? So the ESP that's pointing to the user stack right now, you probably don't want to use that stack. Okay, so there are a few different approaches. One is to allocate a new stack every time an interrupt occurs. Okay, and allocation, as we're going to see later, memory allocation is not a very, very fast process. Okay, because you need to look for some space for you to allocate a data structure that's big enough, for what you need. And the stack space is actually pretty big. Okay, every time you need a stack, well, it's pretty big, right? So therefore, this might be very slow. Okay, you can have one stack shared by all interrupt handlers, right? So we do see that. Okay, when I talk about the interrupt stack, well, that's a stack that's shared by the interrupt handler, but that stack is only used when the interrupt is disabled. Okay, so it's really not that stack that we're talking about. So normally, people will actually not do something like that in their operating system implementation. Okay, what's commonly done is that the interrupt handler is borrow the stack from the thread. It's going to borrow the kernel stack from the thread that's currently executing. Okay, so that's the most common scenario. Okay, so the pictures sort of look like this. Okay, if you are executing in user space, right, that means that this is your user stack. Okay, and then over here they said that, well, that user thread has a corresponding kernel stack. Okay, why is that? All right, I mean, you're executing a user space. Okay, why should the kernel reserve a stack for you? Okay, so that when you switch from when you make a system call, okay, your user thread is going to transition into the kernel thread, and that kernel thread is going to have a stack, right? Okay, so we're going to sort of pretend that even though you didn't really switch to, you didn't really make a system call, but if you were to make a system call, which stack will you use? Okay, so there's going to be a kernel stack for the corresponding user thread, right? Okay, so you can actually identify, the kernel stack for this executing user thread. All right, so we're going to see different implementation of the kernel. Some implementations say every user thread has a kernel stack. Some people say, well, every process has one kernel stack. Okay, so you can use different implementation. But when you can identify a thread, you can say, if this thread trapped into the kernel, what stack would it get? That's going to be the stack I'm going to borrow for my interrupt handler. Okay, so in that case, if this is the current user stack, okay, if you're currently executing code, executing user code, so the kernel stack is not being used, right? Okay, if I'm currently executing user code right here, right, the stack pointer is going to point right here, EBP is going to point right here, I'm not using the kernel stack. Okay, so the kernel stack is completely available for you to use. Okay, so therefore you can just borrow it, okay, and service the interrupt handler. When you service the interrupt, you're executing kernel code. Okay, so you need a stack to execute those C code. When you're done, you pop up everything off the stack. Okay, so if the kernel stack is not being used, when you're done with it, the kernel stack is still not being used, and you can safely return back into the user code as if nothing has happened. Okay, so therefore, in this case, yeah, you save the context and you can restore the context. When the user thread continues to execute, nothing has changed. Okay, so therefore, it's perfectly okay to borrow the kernel stack at that point. Okay, what if that user thread has already made a system call? right? And now that thread is executing inside the kernel. Okay, so therefore, in that case, the kernel will have a stack over here. And again, as we saw before, right? What do we have over here? We have the interrupt handler. We have the system call handler. We have the write handler, right? So over here, we're calling write. Okay, so now the kernel is actually ESP is pointing right here. Okay, and now we're going to borrow that stack. How do you borrow that stack? Well, you just push right on top of it. Okay, so you suspend the kernel thread that's executing the write handler. Okay, and then you just, you just make it as if the write handler called this function to handle the interrupt. It's as if that has just happened. Okay, so therefore, you're going to put interrupt handler number 1's frame right on top of it. What if you get another interrupt? Okay, so you're servicing, let's say you're servicing a keyboard interrupt, and the keyboard interrupt is a low priority interrupt. Okay, then all of a sudden something much more important happened, like some packet coming from the internet, okay, or something coming from the disk. They're much more higher priority than the keyboard. Okay, so therefore you have to interrupt what you're doing. Okay, so in that case, you're executing code, and this is the stack the kernel thread is using to execute the interrupt handler. Okay, now we follow the same rule, right? We're gonna, we're executing the kernel. We're gonna borrow the stack from that kernel thread. Okay, so therefore you are right here executing, that particular stack. So you push on top of that right away. Okay, so maybe this one is the keyboard handler. Okay, and now you have the network handler right here. Okay, and you start executing code using this as the kernel stack. All right, and then what happens is even higher priority interrupt happens. All right, for example, the clock interrupt happened. I think the clock's are at the highest priority interrupt. Okay, the clock is going to come interrupt, and then you're going to build another stack frame on top of it. Okay, is that okay? I mean, is it okay you borrow a stack like this? Well, turns out if you follow some rules, then it will be okay, right? So what happens is that if you're executing the clock interrupt, is the network interrupt allowed to continue? Are you allowed to switch to the network interrupt? Right? Now we have multiple threads running, right? We have the one kernel thread executing this. Well, actually, we have 4 kernel threads. We have one kernel thread executing using this stack frame, one kernel thread using this stack frame, one kernel thread using this stack frame, and one kernel thread using that stack frame. Can we allow this thread to execute? The answer is no, right? If the network thread starts to execute again, what if it calls another function? If it calls another function, it's gonna, write into the stack frame that's currently used by the clock, the clock thread. All right. So the rule is over here is that if we are executing a higher priority interrupt, we're gonna make sure that none of these interrupt handler continue to run. Okay. So every interrupt handler has to run without completion. Has to run till completion without switching to another, kernel thread. All right, so this only works if we follow that rule. Okay, so then when the clock interrupt completely finished, it's going to pop up this guy and it's going to return back to the previous context. And what is the previous context? The previous context is the network interrupt. Right, the network interrupt is going to execute till completion. When it finishes, it's going to return back into the previous context. In this case, it's going to be the keyboard interrupt. When the keyboard interrupt, when it finishes, it will return. It's going to back into the thread context for the kernel thread that's supposedly handling the system call for write. Okay, and eventually when this guy finishes, again, it's going to restore context back into the user space. All right, so over here it's the same concept, right? You save the context, you restore the context, and you make sure to restore back to exactly where it was, and not allowed one kernel thread to corrupt the memory of another kernel thread. Okay, then the scheme will actually work. Okay, so that should work very nicely. That's why this scheme is the most commonly used scheme. All right. Okay, so over here it points out it's very important that any interrupt handler they can be interrupted by a higher priority interrupt. Okay, otherwise they have to execute till completion before returning to the handler of a lower priority interrupt. Okay, you can even view that this is the kernel stack frame right here. Is this an interrupt? Yes, it's a software interrupt, right? Remember, trap is a software interrupt. So this guy is executing over here, well, because it's executing a software interrupt. Okay? So this is really a low-level, low-priority interrupt handler. So they basically all follow the same rule. All right? So that's why the operating system make it a little simple, because everything is following the same rule. All right? Okay, so how do you specify, interrupt, how do you specify interrupt priorities? Okay, there are two approaches. One is to use some hardware, register to implement a bit vector. Okay, so I think Intel, you can handle up to 128 interrupts. So they have a vector of 128 bits. Okay, I mean, I think that's the old Intel. I don't know what the current Intel can handle. Maybe a lot more interrupts. Okay, so you can use a bit vector where every bit represents whether one interrupt level is enabled or disabled. Okay, so that's using a hardware register. So this one, you're going to actually load this register from memory into the CPU. Okay, and the CPU know that, okay, so this interrupt is enabled because they're equal to 1, and this other interrupt is equal to 0. Okay, so if any of these interrupts is going to come, when the interrupt enable bit is equal to 0, that interrupt becomes pending. Okay, so one thing actually interesting, right? We saw the picture over here a while back. CPU has a signal coming in called int. Okay, this is a single line. How does 128 interrupt comes into one single line? Okay, so all these interrupt, 128 interrupt, they're all together. So if any one of the interrupt happens, then this interrupt is going to be a 1. If none of the interrupt are happening, then this guy is equal to 0. Okay? So when this guy comes to the CPU actually will be able to tell, using some other mechanism to tell which one, and that's usually done in hardware, which one is actually interrupt the CPU. Okay? So therefore, it knows that this guy is pending, so therefore, you're not going to execute an interrupt service routine for that interrupt. Okay? If it's this guy, then interrupt is enabled, then you will go and execute the interrupt service routine. All right, so therefore, in your operating system code, you got to make sure that this thing is set properly. Okay, if I'm servicing the network interrupt, I got to make sure that any kind of a lower priority interrupt, they all get set to 0. Okay, only the higher priority level gets set to 1. Okay, so you end up setting a lot of bits. So that's really annoying in the code. You get set a lot of bits, right? So this is really not popular anymore. Okay. These days, people use the hierarchical interrupt level. Okay, so the idea over here is that the interrupt, you just specify one number, and that's the interrupt priority level. Okay, so this is just a single number. Okay, if you say IPL is equal to 20, okay, that means that everything from interrupt priority level 0 to 20, they're all blocked. Okay, if you're setting interrupt priority level to 20, that means that everything below here, from 0 to 20, they're all blocked. From 21 and above, they're all enabled. Okay, so this way, if the network interrupt is at 52, right, so interrupt, you just say IPL is equal to 52, then it's going to block off everything below 52, basically block off anything that has a lower priority level than a network interrupt, and the clock is way up there at, at 128 or 127 or something like that. All right, so this way, using one number, you can actually do that. Okay, so sometimes what goes into the hardware abstraction layer is to convert this into this, because the actual processor, if they're implementing something like this, but the operating system prefer to deal with IPL, then you have to convert this, the way you're dealing with IPL to something that the hardware can handle. So in this case, if you set this guy to 52, basically you have to go to you have to go to the bit vector, turn everything from 0 to 52, they'll turn them all to disable, and enable all the one above it. Okay, and then you set that into the processor. All right, so again, these things can be converted from one implementation to another. When you look at the Unix kernel in our kernel assignment, we're going to see that they use the abstraction that you set IPL level to block out all the lower level interrupts. All right? Again, this is sort of the common approach in the operating system. All right, so we're done with context switching. Okay, so please make sure you understand all the magic that's happening to see how this whole thing works. And later on, when you look at the kernel code, you actually are given code to see how are some of the magic that are implemented exactly inside a sort of a toy kernel. All right. Okay, the next thing we're going to look at, it's also still in chapter 3, is how input and output are done. So this is talking about how do you interact with devices. Okay, devices are keyboard, mouse, disk, network, all the hardware that are connected to your CPU, right? They're all devices. So how do you talk to them? Okay, so we're going to describe, in modern days, we don't, use, Intel processor has instruction called I/O instructions. Okay, they are in by a number or out by a number. Okay, so these are, designed to be used as dealing with devices, input and output. Okay, but modern day operating systems don't do that anymore, or hardware are not built anymore like that. They use something called memory map I/O. Okay, so these instructions, even though they are still in the processor, but mostly they are used to deal with particular chips that are sitting right next to the processor. Okay, and most of the time when you talk to devices such as keyboard, mouse, and stuff like that, remember the picture is like that, right? Here's your CPU, here's the bus, right? And here's memory, and then here's keyboard, mouse, disk, network, or something like that. They all connected via the bus. Okay, so what you do is that in order for you to access these devices, you talk to them via memory addresses, and the operations that you use is read and write, right? But the idea of in is like reading from an I/O device. So what you do is that you can just read from a memory address, and the result is that you're talking to a device. When you wanted to perform an output operation to write to a device, now instead you use a write operation to write to a memory location, and that will map to a particular device. Okay, so that's why it's called memory mapped I/O. You use memory addresses that get mapped into I/O devices. All right, and there are two different kinds. We're going to talk about what these things are. And then we're going to sort of briefly, there's one slide to talk about different kind of I/O architecture that's really not used very much these days in general purpose computers. Okay, and then we're going to talk about some other software issues. So first, we're going to look at hardware to understand how the hardware works. Okay, and then the operating system abstract away, provide a different kind of abstraction. All right, what does a computer look like? Okay, so this is what a computer looks like. It's a bunch of chips. And then, so what happens is that this is a computer. Okay, inside the computer, there are many, many boards. Okay, one of them might be a CPU board. One of them might be an I/O board. The other one will be a disk controller board. The other one will be a network interface board, etc. Okay, so all that devices, they're on boards. Maybe multiple devices will be sitting on one board. Okay, and then at the bottom over here, this is the bus. Okay, the way that you communicate from your CPU to your memory is going through the bus. So what happens is that every one of these boards kind of look like this. At the bottom, they have these metal fingers that they make electronic contacts with other boards. Okay, so you take this thing. At the end, at the bottom over here, there's the board, and the board, there's the bus, and the bus sits on, the bottom is called the backplane. All right, so these metal fingers get plugged into the backplane, and that's how they make, so all these boards go into the backplane, and that's how they make contacts with all the other boards. So the backplane is wired together so that one signal is connected to the other signal that are sitting at exactly the same place on the bus. All right, so these could be addresses. On the other side, there's some other fingers. Could be data, and then over here is read and write, interrupt, and all that kind of stuff. All right, so every one of these metal contacts, every signal has a name on the bus. Okay, so the manufacturer published standards for what kind of bus you have, so that you can build these boards, and then you can have boards from different manufacturers, and they will all be able to talk to each other if they all follow the same protocol. Okay, some of the protocols are, in previous slide over here. Okay, you have multiple devices sitting out here, right? So if this device somehow it wants to talk to the memory all by itself, okay, then you got to make sure that the CPU don't talk to another guy, another device at the same time. Right, because there's only a single bus sitting right here. If both people try to talk at the same time, well, then you're going to have a collision on the bus. Okay, and that's really no good. Okay, so all these, board manufacturers, they have to implement their board to follow certain protocol, certain bus protocol that are specified for those bus standards. All right? So this picture is this computer is LSI-11, is the processor for PDP-11, which is a very popular processor very popular machine that was manufactured by Digital Equipment Corp. Okay, Digital Equipment Corp, they went out of business. They got purchased by Compaq, and Compaq merged with HP. And that's what we have now. All right, so the board is connected over bus. There are many bus standards: Unibus, QBus, etc. Every one of these bus standards might tell you different number of fingers that you can have, how wide these things are, what they look like, and where they're supposed to be. Okay, so we're not really going to get into any of these details. You just need to understand that this is how all the different boards connected together over the bus. Okay, and the bus is shared by all these boards. All right. Okay, so we're going to draw the simple picture, right? Here's the bus. Okay, you have the CPU right here. You have memory, and then you have the devices. The devices don't get connected directly to the bus, right? They go through these controller. So when I say that these boards are networking, well, it's a network interface card, right? Because or the network interface controller. The disk the disk board that goes in there are disk controllers. Okay, so in that case, on the other side, so over here is the bus. On the other side are connectors that you actually connect to the physical device. Okay, so I don't know if you can see any of this thing over here. This might be sort of a CPU board or memory board, so there's nothing to connect to. But if this is a networking board, then on top, that's where you're going to see these Ethernet sockets that you can connect to them. Okay, so this is how some of these boards has tons of wires coming out, so you can connect to disk, connect them to the internet, and things like that. All right, so every one of these things are called controllers. Okay, over here I also draw a controller for memory. Usually memory are a little different because memory is really not a device. Okay, memory you can write directly into memory. You can also directly read from memory. Okay, for things like keyboard, how do you talk to a keyboard? Okay, so what happens is that when you press a key on the keyboard, okay, the keyboard actually is going to generate a character code. The character code gets stored on the keyboard. Okay. And then in order for you to retrieve, to say, well, what key was pressed? Okay, you actually have to talk to the controller, and the controller will go to the keyboard and take that character out from the keyboard and then send it to you. All right, so it's kind of a multi-step operation. So when you press the key on the keyboard, normally what happens is that you will generate interrupt into the CPU. Okay, the CPU says, I'm going to invoke the interrupt handler, like we said before. Lots of stuff happened. Eventually, you invoke the keyboard handler. The keyboard handler will talk to the keyboard controller to say, what was just pressed? Okay, and then it will say, I have finished reading that character. Now you are ready to press another key. Okay, so it's going to talk to the controller by reading from it to see what key is pressed, and then it's going to write to the controller and say, now go ahead, and then, you can read another character. All right, so this one to read and write on these devices. Same thing with the disk, okay? What you do is that the CPU will tell the disk to say, hey, start reading from a certain place on the disk for me, and then when you're done, interrupt me. So at that point, what it will do is it will write to the controller, telling what to do, and the controller will start off the disk. When the disk eventually finished, the reading, what it will do is it will interrupt the processor, and the disk controller, in the disk interrupt handler, what it will do is that it will come back to the controller to say, okay, where's the data? Okay, and then it will read, it will start reading the data off the disk. Okay, so the controller, these are the boards that are sitting on your machine. They will have buffer space sitting on the controller. Okay, so later on, what you can do is you can actually read the data off of the controller. All right, so the networking card, they all work the same way. So by reading and writing to the controller, you'll be able to tell the controller what to do and also get the data from the controller. All right? Okay, so we're going to talk about these two different ways of dealing with the controller. Okay, so we're going to assume that we're using memory map I/O. We're going to use memory addresses that map to I/O device addresses to talk to these I/O. Okay, so what we're going to put out here is that we'll pretend we're reading from memory or writing to memory. Okay, but the address that we put over here will bypass the memory devices. The memory over here, we draw there's a controller, but the idea over here, there's some hardware to say that, oh, these read and write does not map into my address range, so they're not for me. So I'm not going to respond to it. The other controller work exactly the same way. Depending on what address you put out here, if I want to talk to the keyboard controller, all the other controller will look at the address and say, oh, these addresses are not for me. Okay? Only the keyboard controller will know that this address is for the keyboard controller. So the keyboard controller usually doesn't have too many addresses to deal with. Maybe it has 8 addresses, okay, to deal with. So what it will do is that it will look for these 8 addresses on the bus. If the addresses are within this address range, then it will respond. Otherwise, it won't do anything. Okay. Other guys, the controller for the display maybe has a lot of memory locations. Okay, because you want to be able to transfer data directly into the display. Okay, so therefore this one has a high address range. Okay, similarly for this controller, there's a small address range. All right, for the disk, it's going to be a medium address range compared to the display controller. All right, so you use memory map I/O to talk to these I/O devices. Okay, so what is program I/O? Okay, the program I/O means that whenever you try to talk to the device, you have to do that explicitly. Okay, anything that you want from the device, you have to go talk to the device. Says, hey, what have you just done? What is the memory location? What is the data in this particular memory location? Okay, so that's called programmed I/O. Okay, so normally when you talk to keyboard are really slow devices. So when you talk to slow devices, you can actually use program I/O. Okay, so over here, if you want to read something from the keyboard, you're going to use a memory map I/O to perform an I/O read. And then, if you want to put something into memory, so for example, right, you read some data from the keyboard, but you want to sort of remember what data you read, so you're going to write it into memory. Okay, wouldn't it be nice if the keyboard controller can write directly into memory? Okay, that will save you, this, program I/O operation, right? Because if you want to do the same thing using program I/O, you have to read from the controller and you have to write to memory. Okay, that's 2 operations on the bus. Okay, versus, this guy can do it by itself, so that's 1 operation. Okay, so certainly program I/O is a little slow. Right? Similarly, if you want to transfer data from the memory to the controller, if you're using program I/O, then you have to read from memory and then write to the controller. Okay, so program I/O is okay for slow devices. Keyboards are really slow devices, right? Because people who are not typing, they're really, even though if they're very fast typists, but compared to the speed of the computer, it's really slow. Okay, so it's okay to talk to the keyboard using program I/O. For things that are faster, right? The way you talk to them is using both program I/O and something called direct memory access. Okay, direct memory access, basically for these devices, they can transfer data directly, right? That's what direct means, directly into memory. Okay, so what happens is over here is that if you want to, say, tell the disk to transfer data from one place to another, so inside the controller, there's a buffer, right? The buffer can be 8 kilobytes long. Instead of reading everything 1 byte at a time and transferring into memory, you can tell the disk to say, hey, you do it. Okay, so what happens is that you're going to use program I/O to tell the disk controller to try to write, to transfer data from this buffer onto the memory. Okay, so you give instruction using program I/O to a direct memory access devices to tell it to do direct memory access. Okay, as a result, what's going to happen over here is that the disk controller, it's like a CPU. Okay, the disk controller is an intelligent controller board. Okay, it has a CPU on it, so therefore it can just transfer data from the buffer over here directly into memory. Okay, it knows how to communicate over this bus. All right, so this guy actually knows the protocol of the bus, so therefore it can transfer data directly into memory. Right, the keyboard controller is kind of like a dumb controller. It doesn't really know how to get on the bus, so therefore every time it needs to transfer data into memory, well, the CPU has to start a cycle on the bus to read from the keyboard into memory and then copy that onto memory, or go the other way around. Okay, so these controllers are much more sophisticated because they have CPUs on them. All right, so now you know that inside, along the bus, there are actually many CPUs that are all talking over the same bus. All right, so this guy can actually do direct memory transfer, and when it's done, what's usually happen is that it will send an interrupt to the processor saying I'm done. Okay, and now what the so this guy, does the CPU know that the data is in memory already? Well, it knows if it gets an I'm done interrupt, right? If the I'm done says that I'm done, but it was interrupted because this failed or something like that, the CPU also knows. Okay, so what happens is that when it gets the interrupt, the first thing it has to do is to, again, talk to the disk controller to say, what's your status? Was the stuff that I asked you to do last time, did you finish it? If you finish it, then I know exactly where the data is because I asked you to put it there. Okay, so therefore at this point, the CPU knows that the data is over there, and this might be a memory location for the user process or for the kernel process, depends on how things are done. Okay, so the disk controller basically transfers data directly into the buffer inside your kernel code, or even the buffer inside your user process. All right, so this actually can magically appear in the user buffer space when this is done. Okay, if you do things very carefully. All right, so this clearly, if you have 8 kilobytes to transfer, this is much faster than program I/O, doing it 1 byte at a time. Okay, so that's why this is sort of preferred. All right, so the abstraction for the devices, okay, as far as the operating system is concerned, is that every program I/O devices, they all look the same. Okay, they have a bunch of addresses that you have to write to. Okay, so over here, this I/O device has 4 memory addresses that you can read and write from. Okay, there are 4. So over here, they're called registers, even though you write to memory locations. So control register, status register, read register, write register. They're all memory addresses. Okay, and you read and write these guys 1 byte at a time. Okay, so for example, you can write to the control register. Okay, or you can read from the, you write to the control register, or you can read from the status register. Okay, when you read from that status register, the information that you can get from a PIO device are whether the device is ready to be read or the device is ready to be written to or not. Okay, and all the other stuff, they're just garbage. Okay, when you write to the control register, you can tell the device to go ahead and read, go ahead and write, or you set these additional bits to say that, well, when you're done, should you interrupt me or not? Okay, so some of these I/O devices, actually, you can say, well, when you're done, don't interrupt me. Okay, I'm going to come when I'm good and ready to read your status register to see whether you have finished reading or writing or not. Okay, so these 2 guys are optional. They don't have to be set. Okay, but when I'm ready to read, I'm going to call this one. All right, and the other register are the read and write register. So these are the data register. Okay, when I try to read the data, once I know that I'm ready to read, I can just read this memory location. Okay, and this memory location is going to return me 1 byte of what's actually inside the controller. Okay, if I want the controller to do something, what I can do is I can write the operation code, for a particular operation for that controller, write it into the write register. Okay, and then I will say go write. Okay, I'm going to write to the control register to say, hey, device, please read my instruction. I just asked you to do this. Okay, so this code represents some kind of operation for that device, and I can tell the device to go do it. Okay, and when the device finished doing it, this bit over here will tell the device whether to interrupt me or not. All right, and then I can perform the next one. If this bit is not set, that means that I have to keep holding this particular bit called ready to write before I can tell this guy to go ahead and write. Okay, otherwise that means that device is busy. I really shouldn't write to it. Okay, so the CPU need to follow certain protocol to talk to these PIO devices. All right. Okay, for DMA, okay, so DMA, basically you're going to program these devices to tell them to transfer data from the device into memory. Okay, so therefore you actually got to give it, hardware addresses for data to be transferred to. Okay, so in this case, the number of registers increased because you're going to have memory addresses to tell it where to transfer data to and from, and then also over here there are device addresses. Okay, and for a 32-bit machine, these addresses are 32-bit long. Okay, so therefore we need 4 bytes, for the addresses. Okay, so 4 bytes over here for the memory address, 4 bytes over here for the device address. Okay, and then the other ones are very similar. Okay, when the device is ready, we can actually read the status register to say whether the device is ready or not. If ready is equal to 0, that means the device is in the middle of doing some sort of operation, transferring data, from one place to another. Okay, And when we tell the device to go ahead and do something, we will write, we'll have the opcode, the operation code written over here, and we're going to set this particular bit to say, go ahead and do that. Okay? So this operation code might be transferring data from memory to the device, and a different operation code will tell it to transfer data from the device to memory. Okay? And then we also need to tell it, when you're done, to interrupt the CPU or not. All right, so these are the basic abstraction for you to, in the operating system, to talk to the devices. So every device, they all look pretty much the same to the CPU. They just have different registers. And also these operation code are different for different devices. All right, so that's, that's pretty much it. All right, so the direct memory address. So, if you look at this picture again, okay, this opcode, okay, when you need to tell the disk controller to do something, who's putting this opcode there? Right, I mean, clearly the user program cannot do that, right? The user process, they don't have the privilege to talk to devices. So the operating system needs to do that. How does the operating system know that for this device, for this device controller, 3 means to, transfer data from here to there, and for the other manufacturer, 3 means something else? Okay, so the operating system is going to know a lot of stuff, right? So that's really too complicated. Okay, so who should know what opcode to write over here? Okay, so the idea here is that, whoever who plugged the device into your machine, that guy should be writing the code, right? Because that guy knows that for this particular device, 3 means this, 5 means that, 7 means something else. Okay, so the operating system really doesn't want to know how to do that. All right, so that piece of code is actually called device driver. Okay, so every piece of hardware comes with a device driver. The device driver is the one that knows this interface of talking to that particular device. Okay, so in that case, every device driver will actually have a different thing to use. So why have a standard? Okay, so that different device manufacturers, they can actually interoperate, because if they all follow the same standard, then everything will work exactly the same way. Okay, so every device vendor will have different opcodes. Okay, so the operating system doesn't really know what the opcode is, and the operating system shouldn't care. Only the device driver needs to know. Okay, so now we sort of go to this particular picture. Okay, so the device driver is a piece of software. Is the device driver part of the operating system? Yes, right? Because it's executing privileged instruction, they need to access the bus. So this code that is executing in the device driver, they're all privileged operating system code. Okay, so actually when you download Linux, Ubuntu 12.04, okay, it downloads this ISO file, really big, right, 700 megabytes. About 70% of that code is device drivers. Okay, because Ubuntu Linux need to run on all these different kinds of hardware. So when you download the operating system, most of the stuff you're downloading is not the operating system kernel. It's actually device drivers. Okay, every major operating system, when you get an upgrade for Microsoft Windows 8, okay, it's probably 80% of that code is device drivers, because Microsoft Windows run with all these different kind of devices. All right, so these codes need to execute in the privileged mode. So of course, we've got to make sure that these codes are bug-free. Otherwise, your operating system is going to die. Okay, because eventually when I call, write, right, I need to write to the disk. Okay, so over here, this picture shows you that, for a device driver, okay, the device driver is a, what is device driver? Right, it's a piece of code. Okay, this piece of code has an array of function pointers. Okay, so device driver interface is an array of function pointers.
The time
is 14
so
basically
o'clock.
Over here, once these code get loaded into the operating system, the function pointer will point to the code for this particular device. Okay, so therefore, if you want to read from the device, basically you make a function call, passes the arguments of this for read, okay, and then you're executing device driver code. All right, so therefore, at that point, you're in the operating system. You have a write handler. So the write handler, that we saw in earlier today's lecture, that handler is going to eventually call the device driver's write handler. Okay, because potentially, if you overwrite the disk, there might be multiple disks connected to your system. They're sitting on multiple disk controller. Okay, so therefore, for this disk controller, you might invoke a different driver than another one. Okay, so therefore our write handler in the operating system is sort of the generic write handler. It needs to find out which device to use, and then it will invoke the particular device driver's write function for that device. Okay, so therefore these are function pointers. So when you invoke this particular function indirectly via the function pointer, you will run this particular code that knows how to talk to the hardware device. Right over here, this is the physical device. Okay, so this guy knows how to use the write program IO or DMA a register in order to communicate with this device. Okay, so these rewrite, they all handle this thing. Okay, when the device has an interrupt, okay, it generates interrupt into the processor. Again, we go through that procedure. Eventually, we go to the interrupt handler. The interrupt handler, where's the interrupt handler? Well, the interrupt handler is part of the device driver, right? Because only the device driver that are written by this manufacturer knows how to talk to this device. Okay, so therefore, that code must be part of the interrupt handler. Okay, sorry, that code must be part of the device driver. Okay, so again, from the code that we saw, eventually, when you go to a particular interrupt handler, you're gonna start with the device-independent interrupt handler that are in the operating system kernel, and then you're gonna switch to using indirection, switch to a device-dependent version of the interrupt handler, which is part of the device driver. Okay, and inside this interrupt handler, what does interrupt handler do? Interrupt handler, and again, they need to be as small as possible, right? Just like our signal handler in warm-up number 2. And the main thing that it needs to do are two things. One is to unblock a thread that's waiting for that interrupt to be completed. Okay, so that is usually done in the device-independent part of the interrupt handler. Okay, and then what it needs to do is to start the next I/O operation for that device. Okay, so inside the kernel, there's going to be a queue for this I/O device. Okay, they are these jobs over here waiting, to be done. So if this is a device for the disk, maybe you have 20 threads that belong to 20 different user processes. They all want to read from the disk. So all these read requests are queued up over here into this device queue. So when you get an interrupt, what you need to do is you need to take the next job from the head of the queue and then start off an operation on the disk. So what does this remind you of? Like the server in warm-up number 2, right? Okay, whenever the server becomes busy, it goes to the head of Q2, take a job, and then sleep. We use the sleep to, as if you're reading or writing to a device. Okay, if we're doing a packet, token bucket buffer, then we are simulating some kind of a networking device. So, the code for the server is actually the interrupt code over here is going to start off, sending out a packet across the internet. All right, so that's the real story of warm-up number 2 is trying to sort of get you introduced to this kind of concept. All right, so this is the queue over here. So inside the interrupt handler, two most important things: unblock the thread, right? So there's one thread that's waiting for this device to get finished. When that one is done, that one needs to get ready to execute, right? Ready to be eligible to be switched into. Okay, so then another thread can say switch to this thread. Okay, so you need to unblock that thread from waiting for I/O into eligible for running inside the CPU. And then the other thing, you need to take the first job of this queue and start off the I/O operation. Okay, so these two things are done at the device-independent, interrupt handler. Okay, but then unblocking this thread doesn't really involve the device-specific part. But then when you try to start off the next operation, then boom, you are here again executing this code, telling, by looking at the first job, whether you want to read or write from the disk. So therefore, you either call this routine or this routine. And again, that becomes device-dependent part of the interrupt handler. All right, so I hope you see how all these things are connected together. All right? All right, so C++ sort of look like this, right? If you want to have a device-dependent and device-independent part of a disk interface, all right, you might have something like this. You have a disk that declared like this, and you have all the read and the write, all these interrupt routine. Since they are device-independent, so they need to be implemented in the subclass of the disk class, right? This class is called disk. So this is talking to a generic disk. Okay, RIC, generic disk. Okay, so what does the generic disk do? Right, like I said before, inside the interrupt handler, you need to unblock a thread, okay, and then take the next thread off of the device queue, and then find out what it needs to do, and then to invoke the correct read and write routine for the device dependent device. Okay, so therefore that code that's doing that logic is going to be sitting in the device independent part. All right, so if you do this in C++, it's a very good fit. Okay, because we can have the generic code run at the disk class, okay, and then we can actually have subclasses of disk that will implement independent vendors read, write, and interrupt routines. So how do we do this in C? Okay, if you do this in C, again, you got to do using indirect indirection. Okay, so therefore, hold on, where's that slide? Oh, actually, that slide doesn't belong here. Okay. So the point over here is that this particular mechanism of subclassing and then call a device-specific implementation of a particular disk, that's called polymorphism. Okay, so this is C++ polymorphism, and people who know C++ know how it works. So what we're going to see is that we're going to actually see polymorphism implemented in C. Okay, so how do you do polymorphism in C? Right. So what happens is that you're going to have a data structure. You have the generic routines over here, okay? Generic routines are up here, okay? And then the device-dependent routine, what you can actually do is that you can have function pointer to point to those functions. All right, so in this way, the read, write, and interrupt, they will be function pointers that points to where these functions are through another level of indirection. Okay? So maybe these guys are already function pointers. Over here, there's a function pointer that point to function pointer. Right, because once you have an indirection, you can have multiple indirections and can go on forever. All right, so I can actually create a data structure over here to hold all the device-dependent stuff. So whenever I activate a device controller, right, because I know, the operating system decided that this particular device is connected to my machine, so therefore I have to load the device controller for that device. So what does loading of that device controller mean, right? That means that you take the code for the device driver, put them into memory, and then you point to them in this data structure. All right, these are function pointers, so you can point to those guys. So now this thing knows how to talk to that particular device. Okay, and in the generic code over here, I know that if I have to do read and write, I have to invoke these functions indirectly through one level of indirection. I can't just call them directly. I can't call read and write for the device-specific part. I have to actually call them indirectly. All right, so that's how C implements C++ polymorphism. All right, and also, I guess the other thing that this slide points out is that this particular code is a little unrealistic over here because we want read and write to be synchronous. Okay, so this is a synchronous interface, and synchronous meaning that you call this function, and this function only return when it's completely done. Okay, so in a real device doesn't really work like that, right? The device have these I/O register. We just talk about how they actually work. So in reality, the read function is not a synchronous call, right? It's you call read and some read starting to happen. Okay, so it's more reasonable to call these functions start read and start write. Okay, because then you have to have another way to sort of figure out that whether the device is ready or not. Okay, so then you have a function call over here. It's called wait. Wait is for that device to be ready. Okay, so again, if you remember the previous, we'll talk about the PIO or the, there's one of the register over there. You can check whether the device is ready or not. Well, that's where you can actually wait for something. Okay, but if you have interrupt enabled, then wait just blocks and wait for an interrupt to get triggered. All right, so in the real device interrupt, more realistic is that you don't have read and write that to be synchronous. You actually have start read, start write, and you can wait for it if you want, or you let interrupt handle, all these kind of conditions. All right, so this is more realistic. The last slide over here talk about a different kind of architecture. This is the only time you're going to see channels. So in this case, these are applications, or these are special machines where the I/O costs dominate the computation costs. Okay, these are special machines that all they do is I/O. Right. So for example, if you want to build a database server, that, the CPU really doesn't do very much. All it does is to, do disk operations. Okay, so in that case, what you want to do is that you might want to create a memory that has multiple ports, that on one side, here's one bus for to talk to the CPU, and over here there are multiple buses for it to communicate with other CPUs. Okay, these are I/O CPUs, or they're called I/O channels. They're special CPUs that can actually perform I/O operation at a very high speed. Okay, so in that case, in order for you to communicate with the I/O controller, what you do is that you will write data into memory, use some kind of a shared memory scheme for the CPU to communicate with each channel. Okay, or another way to go is that you have all these channels also sitting on the bus of the CPU, so you can talk to these channel controller directly and then have them do something, and eventually when they're done, they can send data directly into the memory without going to the CPU bus. Okay, because if you're going to the CPU bus, then you have to make sure that the CPU is not doing something else. All right, so in that case, you will actually have a controller over here for talking to the memory, and over here, every one of these guys will have a different controller. So in that case, the memory will actually have a controller, and this controller is to make sure that you don't access the memory simultaneously. All right, because otherwise, if both the CPU and the channel controller try to write to the same memory location, then that's going to be really bad news. Okay, so these controllers need to be coordinated so that they can, access memory in a mutually exclusive way. All right, there are actually even very, very high-speed memory where you can actually write to the memory devices simultaneously as long as you don't write to the same memory location. Okay, so those hardware is starting to get very, very expensive. Okay, so there are people who has those kind of need. They will use special I/O architecture to handle the special need. But when we talk about general purpose, computers, we don't really use this. All right, so that's why this is the last time you will see this. Okay, so I am done with, I guess the first part of chapter 3. I'm going to skip, let me go to this slide. Okay, so this is the lecture slide here. Loading kind of slow. All right. Anyway, so the next section is, if you go to a textbook, it talks about things like memory allocation and talk about devices stuff. I'm actually going to skip that. The next thing I'm going to talk about is still in chapter 3 about linking and loading. Okay, because we need that concept first before we actually have to talk to devices. All right, so I'm not going to wait for this. All right, so we're going to tell you what's exactly in an executable. Okay, when you compile your program, generate warmup1. What is warmup1? Okay, it's an executable file. What's in it? Okay, because eventually when you call execl, right? Remember, you're going to call execl, right? The first argument of execl is a path to your program. Okay, so this is a system call. Okay, that system call is going to wipe out the current address space and then go to this file and load that thing into memory. Okay, so this is a program that that can actually run, right? So we're going to sort of, so what has to be inside this program for execl to work? Because execl needs to build the address space for the new process, right? Wipe out the old address space. So this guy must have all the information that's required to build a brand new address space, right? And what is an address space, right? Has a code segment, data segment, BSS. In a brand new process, right? You wipe out the old address space, you start a new process. What does the heap look like? It's empty, right? Because nobody has allocated anything, right? So heap you don't really have to worry about. What about the stack? Okay, you got to get ready, and you're going to run one thread in them, right? The thread entry point is going to be main, right? So you got to have one stack that's ready. Inside here, the top of stack, we already know it's not main. It's the startup routine, right? And the startup routine is going to call main. Okay? So you need to, so in execl, that's what execl does. Okay? Go through this guy, prepare this address space, and return, and ready to do what? Okay? So this guy eventually is going to execute, it's going to execute, the program over here, starting with the startup, right? So there's even no main in the stack frame. There's only the startup frame. So you need to set up the static frame. Okay, and then it's going to pretend that it executes an interrupt return. All right, so what happened in this case is that in order for us to execute the first instruction of the new process, okay, we're going to pretend that that guy made a system call, okay? Because otherwise, how are you going to start that process? If you think about it, right, that's the process, we just say exec L, wipe out the address space, all right, so the previous code is completely gone, okay? It's going to execute the first instruction, okay? So the only way to, or the best way to start this particular process is pretend that right before the first instruction, it actually made a system call. Okay, I mean, in a way, yeah, it did make a system call, but the system call wipe out its address space. Okay, so we're going to set everything up as if the contacts are all at the right place, ready to execute an interrupt return.
5 minutes left, Professor.
All right, thank you. Okay, and this interrupt, return from interrupt is going to make you execute in the user space. Okay, and this user space is going to execute the next instruction. And what was the next instruction? Well, the next instruction was saved in a context area, right? Okay, does the operating system know how to set up this context area to fake it so that when I execute an I return, it will return to the first instruction in the starter routine as if it just returned from a trap system call. Okay, the operating systems actually can do that, right? Okay, so therefore, in the end, when you do exec L, right, the last thing that you do inside the operating system is a return from interrupt after they set up all the contacts to pretend that, they just made a system call, and now it's going to return to the first instruction, which execute inside the startup routine. All right, the startup routine, what does the startup routine do? Well, it calls the main function, right? And then when the main returns, it calls exit, right? That's what, so the startup routine is very, very small. It has a small number of lines in there. So the starter routine, the code is also in here. Main is in here. Everything is in the code segment. All right, so basically, in order for us to prepare this address space, this executable got to have all that information. All right, so how do we create the executable over here? Okay, all right, so basically, we're going to make sure that, these things all happen correctly, right? So this is from the last lecture, okay? We're going to look at a sort of a smaller example, okay, to look at what do you have to do to the main program to make sure that when you put it into the executable warm-up1 or warm-up2, that the exec L will be able to load that into memory. Okay, so as it turns out that the code, that what you need to do is that there's a little bit of a tricky code, okay? The code is going to look slightly different from the previous phase. All right, so we're going to look at a much simpler code to start with. Okay, so this one, the main actually does this, has some arguments, okay, has no local variable. All it does return, it doesn't really call anything. Okay, so in this case, what happens is that the code that you generate is very, very simple over here. And this particular code can be put anywhere in memory. Okay, so this code, EIP, can be anything. Okay, so EIP, as long as the point is this location, this code is completely location independent. Okay? You can put this one starts at location 500, it will execute. You put this code in location 50,000, it will also execute. Okay? Why does this code can execute in it's location independent? All right? Because, everything that it needs over here are accessed relative through the EBP register. Right? This function only needs, argc over here. If this guy needs to access a global variable, okay, so over here, let's say that over here you use an x, you say x++, and over here you have in x. Okay, then this code, you cannot really just move this code anywhere and it might work. Okay, because if you move it into the same code, same place as where in used to be, and now in got moved to a different place because your program got bigger. Okay, then 1 minute. Okay, then the memory location that you reference over here will become invalid. Okay, so this code, if it contains memory references to X, then you got to make sure that X points to the right place. Okay, but if this code accesses every memory location using register relative addressing, in this case using EBP, you can plus something, you can minus something. So even if it's a local variable, it's okay because all the memory reference you generate is going to be relative to EBP. Okay, so these memory addresses doesn't really matter. Okay, as long as you have the right stack frame, then they will access the right places. Okay, so the stack frame can actually, this stack frame can also be located anywhere in memory, and this code is going to work. All right, so I'm going to stop here. I'm going to transition into the next case where, you know, the addresses is going to become matter. All right.
This is CS402 on Wednesday, June 11, 2014.